In the last class, we have studied the difference between permanent and electromagnets. Then, how this magnetic field is developed around that current carrying conductor, how to find the direction of that magnetic field, clockwise or anti-clockwise, around that current carrying conductor. Also, some terms used in magnetism. In this class, we will study the similarities and dissimilarities of electric and magnetic circuits, BH curve, hysteresis loop, some terms used in magnetism, and also we will study how to solve some examples. First, we will see the similarities and dissimilarities between electric and magnetic circuits. In the last class, we have studied that magnetic circuit and electric circuits are having so many similarities, and we have also studied some of the terms associated with magnetic circuits. Here, we will just compare one by one of the terms we have studied. See, a closed path of electric current is called electric circuit. Similarly, a closed path of magnetic flux is called a magnetic circuit. The cause of this current flow is this EMF, while the cause of generation of this magnetic flux is MMF, which is created by this current and the number of turns. This resistance R opposes the flow of electric current. Similarly, in the magnetic circuit, the reluctance S causes opposition to the flow of flux. Unit of EMF is volts, while unit of MMF is ampere turns, that is current into number of turns. The value of current I is equal to EMF divided by resistance of the path. Unit of current is amperes. In a magnetic circuit, this flux phi is equal to this magnetomotive force divided by reluctance of the path. The unit of flux is Webers. Current density J of an electric circuit is current I divided by area of cross section of that conductor. It is expressed in amperes per meter square, while flux density B of a magnetic circuit is phi divided by A, that is area of cross section. It is expressed in Weber per meter square. We know that resistance of an electric circuit is directly proportional to length of the conductor and inversely proportional to area of cross section. So, resistance R is equal to L by mho into A, where mho is the conductivity, which is a constant, and it varies for different conductors. Similarly, here reluctance S is equal to length of the path divided by mu into area of cross section of the path. Here also mu is a constant, which is called permeability. Next, we will study dissimilarities between an electric circuit and a magnetic circuit. In an electric circuit, electric current actually flows, while in a magnetic circuit, the magnetic flux shown here actually does not flow. These are just imaginary lines. See here, these conductors, current flows through these conductors, while it does not flow through these insulators. So, as current does not flow through good electric insulators, we can control flow of electric current through a particular path using insulators. While in the case of a magnetic circuit, there is no such insulators to control flow of magnetic flux. Some leakage flux will be always there. Current flows only when there is sufficient energy for current flow. That is, when we are switching off this voltage source, the current flow stops. But in the case of this magnetic flux, energy is required only to create magnetic flux, but not to maintain it. That means even if we are removing this source, magnetic flux remains in it. If temperature is constant in an electric circuit, then resistance also will be constant, while the reluctance of a magnetic circuit is not constant and it depends upon flux density in the material. Next, we will see some effects of electromagnets. Here, one magnetic core is wound with a coil which is having n number of turns and through which a current I is passing. So a field is created around this conductor and total magnetic flux phi t, which is created by the coil, passes through this magnetic core. From this total magnetic flux created by the coil, some of the flux is leaking outside of this core and some are passing through the core. From the total flux created, the useful flux which passes inside the core is only phi, and that leakage flux is phi L. That means the total flux phi T is equal to useful magnetic flux phi plus that leakage flux. That is the magnetic flux that does not flow the intended path in a magnetic circuit is called leakage flux. Leakage factor or leakage coefficient lambda. Leakage factor or leakage coefficient lambda is the ratio of total flux produced phi A divided by useful flux in the air gap. That is only this much. That is the formula can be written as lambda is equal to phi A, which is the total flux, and phi G, which is going through that air gap. Typical values for leakage factor are between 1.12 and 1.25. Air gaps are provided in many practical circuits. See, the flux generated here and coming through this curve can be seen bulging while it is passing through these air gaps. See, it is bulging on both sides. This bulging of flux lines in the air gap is known as fringing effect. Now we will see the relation between magnetizing force H and flux density B. BH curve or magnetization curve. BH curve is a plot of flux density B versus magnetic field intensity or magnetizing force H. For these magnetic materials, relation between B and H is B is equal to mu 0 mu r into H. Figure shows the BH curve for different magnetic materials like cast iron, cast steel, sheet steel, etc. It can be seen that these curves are non-linear. As these materials are having different relative permeability, their curves are also of different shape. Next, we will study what is hysteresis loop. Before going into hysteresis loop, we will see what is magnetic hysteresis. Actually, when magnetizing force is applied, the subject is magnetized, that is, its flux density is increased. When we are reducing that magnetizing force, this flux density still remains in it, that is, this flux density lags behind this magnetizing force. So, magnetic hysteresis may be defined as the lagging of magnetization or induction flux density behind the magnetizing force H. Alternately, it may be defined as that quality of a magnetic substance due to which energy is dissipated in it on the reversal of its magnetism. That is, even if magnetizing force is removed, some energy still remains in it. Next, we will study what is magnetic hysteresis curve or loop. Consider a core which is not magnetized and this is placed inside a coil. When no current is passing through this coil, there will not be any magnetism in this core. But when we pass current through the coil, a magnetic field is produced. It magnetizes the iron bar. That magnetization force H is proportional to the value of current we are passing through the coil. Next, we will plot the relation between that magnetizing force H and flux density B. Magnetizing force H in x-axis and flux density B in the y-axis. So, when we are passing current through the coil, a magnetizing force will be developed, and when that magnetizing force is increasing, the flux density also increases along this curve OA. When magnetizing force H is increased further, we will think this flux density also will be increasing. But it is not like that. At the point A, saturation occurs and the value of this flux density remains the same even if magnetizing force is increased. Next we will see what happens when this magnetizing force is reduced, that is going in this backward direction, reverse direction. When this magnetizing force is reduced, that is in the negative direction, we may think that the flux density also comes along the same curve, that is from A to O. But it is not like that. It takes a different path, that is the path AC. That means even if we have reduced the magnetizing force H, some magnetism remains in the core. The amount of flux density that remains in the core even after removing this magnetizing force is called residual magnetism or remnants of the material, that is this much OC. So we have reduced the magnetizing force to 0, but even then some magnetism is remaining inside this thing. In order to demagnetize the core by removing this much residual magnetism, the magnetizing force is reversed further by reversing the direction of current in the coil. That is, this current direction will be reversed. Now we can see that the curve follows the path CD. At D, the core becomes completely demagnetized. So, the magnetizing force required to remove the residual magnetism from the material is called coercive force or coercivity of the material. That is, this much magnetizing force we have to apply in the negative direction to remove that residual magnetism. The coercive force or coercivity of the material is represented by OD on the curve. When this magnetizing force is reduced further in the negative direction, the curve follows the path DE, and at E it is saturated in the opposite direction. If the magnetizing force is reversed towards positive direction, the curve follows path EFGA, residual magnetism and retentivity. When we have studied that BH curve, when magnetizing force is applied, this flux density also is increasing along the curve OA and it saturates at point A. After A, even if magnetizing force is increased, it remains at the same level. Suppose we are reducing the magnetizing force, it will not be following this path, but it will be reducing along the path AC. This is because the core retains some magnetic flux even after removing the magnetizing force we have applied. The portion OC, that is the magnetism which remains in the material even we are reducing the magnetizing force to 0, is called residual magnetism. That is, residual magnetism is the magnetic flux density remaining in a material even when the magnetizing force is made 0. This is also called remnants. This point C, that is called retentivity, is the power to remain its magnetization even after the magnetizing force is made 0. Coercivity. We know that when magnetizing force is increased, flux density also increased to a certain level and it saturates. After that, when this magnetizing force is brought back to 0, some residual magnetism is there, so that it will not be coming to 0, but it follows curve AC. After that, to reduce this magnetism to 0, the magnetizing force is applied in a negative direction, so that at D, the magnetism of the core becomes completely removed. That is, this negative magnetizing force OD required to bring the magnetic flux to 0 is called coercivity. That is the OD. That is, this much magnetizing force which is required to reduce the magnetism in the material to 0 is called coercivity. The magnetizing force required to remove the residual magnetism from the material is called coercive force or coercivity of the material. Energy stored in a magnetic field. See this figure. Here one battery is connected across this inductance of value L through a switch. When this switch is off, no current will be flowing. That is, I is equal to 0. When the switch is put on, the value of that current becomes the total value depending upon the inductance. Then self-induced EMF in the inductor is E is equal to L into that rate of change of current. That is, this current is switching from 0 to I, that rate of change of current. We know that power is equal to voltage into current. P is equal to E into I. Therefore, energy supplied during the interval dt is dE is equal to power into the time for which that energy is supplied. But P is E into I. Therefore, dE is equal to E into I into that time. Substituting the value of E from this equation, this becomes L into di by dt into I into dt. d by dt of dt is equal to 1. Therefore, this becomes L into I into di. This energy is for a small interval of time dt. Therefore, total energy required to establish a current of I from 0 is, total energy is equal to, we have to integrate it from 0 to I, but dE is equal to L into I di. So, this equation becomes integral 0 to I L I di. We know that integral of x dx is equal to x squared by 2. Therefore, integral of I di is equal to I squared by 2. That is L, which is a constant, into, we have integrated this I, that is I squared by 2, and we have to give values from 0 to I. This becomes L into I squared by 2 minus 0 squared by 2. This becomes 0. Therefore, this equation becomes 1 by 2 L into I square. Therefore, energy stored in the magnetic field E is equal to half L into I square joules. Now, we will try to solve some examples. In example 1, a flux of 0.08 Weber is produced in a solenoid containing 250 turns, which is having an axial length of 20 centimeter. Then, if this solenoid carries a current of 8 ampere, we are asked to find the magnetizing force and reluctance of the magnetic circuit. Solution. It is given that number of turns, that is N, is equal to 250 and the current flowing I is equal to 8 ampere. Therefore, magnetomotive force MMF is equal to N into I, that is equal to 250 into 8. 250 into 8, which is equal to 2000 ampere turns. Length of the solenoid is given as L is equal to 20 centimeter, that is equal to 20 by 100 meter, which is equal to 0.2 meter. Then magnetizing force H is equal to MMF divided by length of the solenoid, that is equal to 2000 divided by 0.2, which is equal to 10,000 ampere turns per meter. It is given that the flux developed is 0.08 Weber. Flux developed is equal to 0.08 Weber. Therefore, reluctance S is equal to MMF divided by flux. Here MMF we found as 2000 ampere turns. Substituting this value here and the value of flux here, reluctance becomes 2000 divided by 0.08, that is equal to 25,000. Unit of reluctance is ampere turns per Weber. Example 2. Here a steel ring having a cross-sectional area of 400 square mm, which is having a mean diameter of 20 centimeter, is given. We have to calculate the reluctance of the ring and MMF required to produce a flux of 500 micro Weber. It is said that we can assume relative permeability, that is mu r, of this material as 1000. Solution. Cross-sectional area of the ring is given as A is equal to 400 mm square. While converting to meter square, this becomes 400 into 10 raised to minus 6 meter square. The mean diameter is 20 centimeter. D is equal to 20 centimeter. That is equal to 20 by 100, which is equal to 0.2 meter. Now the length of the circular path becomes the circumference of the ring. That is, mean length of the ring L is equal to circumference of the ring, that is pi into D, which is pi into 0.2 meter. Here relative permeability of the steel material is given as 1000, that is mu r is given as 1000. Therefore, reluctance of the ring S is equal to L by mu 0 mu r into A. Here L is the mean length of the ring, mu 0 is the permeability of free space, mu r is relative permeability of that steel material, which is 1000, and A is the area of cross section. Substituting these values, this becomes 0.2 pi, which is the length, divided by mu 0 is permeability of free space, which is 4 pi into 10 raised to minus 7 into mu r, which is 1000, into area of cross section is 400 into 10 raised to minus 6. Simplifying this, we will get this is equal to 1.25 into 10 raised to 6 ampere turns per Weber. The flux phi developed is given as 500 microweber. That is, flux phi is equal to 500 microweber. That is 500 into 10 raised to minus 6 Weber. Therefore, magnetomotive force MMF is equal to phi into S, which is equal to flux phi, which is 500 into 10 raised to minus 6 into the reluctance, which we found as 1.25 into 10 raised to 6, 1.25 into 10 raised to 6, which becomes 625 ampere turns. In example 3, we are given a steel magnetic circuit which is having a cross-sectional area of 4 square centimeter and is having a length of 50 centimeter. This is wound with a coil which is having 250 turns. Then when a current of 1.5 ampere is passed through the coil, a flux is developed which is 0.25 milliweber. Now we are asked to calculate the magnetic field strength of this circuit and relative permeability of the material. Solution: it is given that length of that magnetic circuit is 50 centimeter. That is, L is equal to 50 centimeter. That is equal to 50 divided by 100, that is 0.5 meter. Next, cross-sectional area is given as 4 square centimeter. So, A is equal to 4 square centimeter, which is 4 into 10 raised to minus 4 meter square. Number of turns of the coil is 250. That is, N is equal to 250 and current I is given as 1.5 ampere. I is equal to 1.5 ampere. The flux developed is given as 0.25 milliweber. So, flux phi is equal to 0.25 milliweber, that is equal to 0.25 into 10 raised to minus 3 Weber. So first we are asked to find the magnetic field strength of the circuit. We know that magnetic field strength H is equal to N into I divided by L. Here N is equal to 250 into I is equal to 1.5 divided by L is equal to 0.5. Simplifying, you will get 750 ampere turns per meter. Next we are asked to find the relative permeability of this material. We know that flux density B is equal to flux phi divided by area of cross section A. Flux phi is 0.25 into 10 raised to minus 3. A is given as 4 into 10 raised to minus 4 meter square. Substituting these values of phi and A here, 0.25 into 10 raised to minus 3 divided by area 4 into 10 raised to minus 4, which gives 0.625 Weber per meter square. Also, flux density B is equal to mu into H, that is equal to mu 0 mu r into H. Therefore, this mu r is equal to B divided by this mu 0 into H, that is equal to B we found as 0.625. Mu 0 is permeability of free space, which is 4 pi into 10 raised to minus 7. H is this magnetic field strength N into I by L, 750. Substituting these values of B, mu 0 and H here, this becomes 0.625 divided by 4 pi into 10 raised to minus 7 into value of this H, which is 750. Simplifying, we will get this as 663. Hope this class also might have been useful to you. If so, please like it, share it and subscribe it by pressing that bell button so that you will be getting notifications of all my future videos also. Thank you.